To understand switching, we need to look back through the mists of time. After all, the need to send information from one place to another is not new. Electronic communication itself has been around since the mid-19th century and has never stopped improving. Think of the old telephone system that needed an operator to manage a switchboard. When someone needed to place a call, the operator would manually connect the cables to make an electronic path for the phone call. And creating paths is what switching is all about. But it's a little more sophisticated these days. So, stay with me and I'll bring you up to date, piece by piece. We're going to come forward a few decades now to a time when computers are starting to be more common in offices. They started as standalone computers, but they needed to share data, so networking functions had to be added. But unlike the old telephones, creating manual circuits or using physical cables between every single computer was not an option. One solution that they came up with was to daisy chain every computer together. It could be open-ended, which is called a bus topology, or the ends could be connected to form a loop, which is called a ring topology. And this is okay for a small number of computers, but it gets difficult when the number of computers in the office starts to grow. Imagine trying to add a new computer somewhere in the middle. We'd have to break the network apart and insert the computer in there. Also, if there's a break in the cable, the network has now been broken into two separate parts. And in addition to the physical connections, there needs to be a protocol. We've talked about these before. The protocol is an intelligent way of sending data from one location to another, without needing physical circuits like the old phone system. For example, the protocol needs to work out how to share this network, how to take turns sending messages, and how to work out which messages go where. And on top of all this, the network needs to figure out how to handle errors. What happens if two computers transmit at the same time and their messages get all mixed up? This specific scenario is called a collision, and it is a real concern when sharing the physical medium like we see here. Ethernet is a very common protocol, and we've spoken about this before too, but now it's time to add more detail. Ethernet uses MAC addresses to identify each computer on the network. There is one MAC address per network interface, so a router, for example, with more than one interface will have more than one MAC. Each MAC address is always 48 bits long, and it is written in hexadecimal. There are different ways you could write down a MAC address. Both of these that you see here are exactly the same address. They're just written down differently. The addresses are burned into the network card, so they're not something that we can change. This helps to make them unique, which is absolutely required for MAC addresses. To make this work, they're broken into two halves. The first 24 bits is called the OUI, or Organizationally Unique Identifier. And there's an organization out there called the IEEE, and it assigns this OUI portion of the MAC address to the hardware manufacturers. The manufacturers then assign the second half of this address to their products as they see fit. The point behind all this is that there is no two devices, or should be no two devices, across the entire world that have the same MAC address. Now, aside from these MAC addresses, there are also some special addresses. The first is the broadcast address, which is all Fs. No device owns this address. It just simply means deliver this frame to every device on the local network. I say local network, as routers will not forward broadcast frames to other networks. Another type of address is a multicast address. There are a lot of these, so I can't list them all, but you can look them up if you want to. These are also not owned by one particular device. They are used to send frames to a group of devices for a particular purpose. Multicast in general is something that we'll look at in a different video. Ethernet frames follow a well-known format that look like this. There's always a header before the data and always a trailer after. The source and destination are probably the most interesting fields. When a frame is sent, the sender embeds its own source address. And of course, it will have to put the destination address in there too. At the very start of the header is the preamble. This is a fixed pattern of ones and zeros, which lasts for 7 bytes, and this pattern shows that this is the start of the frame. The 8th byte is the SFD, or start frame delimiter. This is also a pattern, although a different one. It is 1 byte long, and that shows that the very next byte will be the destination address. The type field tells us which protocol is in the data section of the frame. Remember encapsulation that we've talked about a few times already? Well, this tells us which protocol has been encapsulated inside this Ethernet frame. These days, these are most likely going to be IPv4 or IPv6. IPv4 is probably the one you're more familiar with, and we'll look into IPv6 some more in some future videos. And at the very end of the frame is a trailer, and this trailer contains the frame check sequence, or FCS. This is used to determine if any part of the frame has become corrupted during transit. When the frame is first assembled, the sender will run a mathematical formula over the frame contents. It takes the result of this and puts it in the trailer. When the frame arrives, the receiver runs the same formula over the contents of the frame, without the trailer, of course. If the result matches the contents of the trailer, then clearly the data is the same as it was when it was first sent. That means there's been no corruption. But if the results are different, then there must have been a change in the data somewhere. That means that the frame is corrupt and it will be discarded. Ethernet will not try to recover this data. However, as we've seen in past videos, higher level protocols like TCP may try to recover the data. In this older style of network, when frames are sent, every device will receive a copy. When a device receives the frame, it will look at the destination MAC address in the Ethernet header. If it owns that address, it will accept and process the frame. If not, it should discard the frame. This raises two problems. Firstly, there's a lot of unnecessary traffic flowing around which uses up more resources. Secondly, this has potential to be a security risk. If every device can see your traffic, then they might also be able to see your private information. The older networks have their limitations, as we've discussed. So around the mid-80s, the idea of a hub was introduced, much like the one we're showing here. This is probably getting a lot closer to what you're used to seeing. It's a box that you can connect your computer to, rather than needing to chain all your computers up. This makes it so much easier to add and remove devices as you need to. And if you run out of ports, you can buy an extra hub and you can daisy chain those to get the extra ports you need. On the inside, hubs aren't really doing anything different. They're still using the same bus network, connecting all the ports in a chain. That means that the ports are part of the same LAN, and any data received on one port is sent to all the other ports. For this reason, hubs are sometimes called port repeaters. So there's a lot of extra traffic flowing around, and every device can see every other device's traffic. Hubs were definitely an improvement, but they haven't added any intelligence or data processing. From a network perspective, they're not much more than a bundle of wires put inside a box, and that makes them layer 1 devices. And as this is still a bus network inside the hub, a device cannot send and receive at the same time. We have a term for this, and that is half-duplex. For that matter, only one device on the network can send at one time. If two devices try to send at the same time, they cause a collision. And because a collision could happen at any point in this topology, the entire network that we're looking at is called a collision domain. And the larger the network, the larger the collision domain. That is, the more devices, the more chances there are of a collision occurring. And the more collisions that happen mean we need to spend more time waiting and resending frames, and that lowers the overall performance of the network. Sadly, in a network like this, we can't just eliminate collisions. But Ethernet, being very clever as it is, can minimize them. And to do this, it uses, I guess it's an algorithm or maybe a protocol called Carrier Sense Multiple Access, or CSMA. There are two parts to this. First, collision avoidance. It attempts to determine when the network is idle, and it will only transmit then. This helps to avoid a lot of collisions before they even happen. But on occasion, two devices will determine that the network is idle, and at the exact same time, they will try to transmit. And yes, you guessed it, that causes a collision. So, the second part is collision detection, which is able to, just as it sounds, detect these collisions. When the two devices detect the collision, they both decide to wait a short, random amount of time before attempting again. And because these times are random, they shouldn't be the same, which lowers the chance of them both transmitting at once, which lowers the chance of collisions. Right, if you've been watching these videos for a while, you'll know that I like to challenge you with a few quizzes. This time you may need to do some of your own research to work some of these out, but the time will be well spent as it will deepen your understanding. My answers are available on the website as a thank you to Patreon supporters. Well, we've seen that hubs were an improvement, but they still do have some downsides. All devices are in the same collision domain. They use half-duplex communication, and data is sent out every single port. All this adds up to limiting how far the network can grow. So, to address some of these concerns, network bridges were created. We can take our large bus topology network, and we can break it into two or more smaller networks. We then connect them using a bridge. The bridge is a physical device that would look very much like a hub, maybe with fewer ports. Typically, hubs would connect to bridges, and other devices would connect to the hubs. While all of this is still in one network, or LAN, we have now broken this into smaller segments. Unlike hubs, bridges have a bit of intelligence. They keep a table of the network's MAC addresses in memory, as well as which segment these MAC addresses belong to. When a frame arrives at a bridge interface, the bridge looks at the destination MAC field in the Ethernet header. It will then look at its MAC table, and it will see which network segment this MAC belongs to. It knows about each segment as it has an interface connected to each one. If the MAC address is in the same segment that a frame came from, it will not forward the frame on. It assumes that the sender is already closer to the destination than it is, so it doesn't need to forward the frame on. If the MAC address for the destination devices is on a different network segment, the bridge will forward the frame out. If there's a hub connected, that then will of course replicate its frame to all of its ports as normal, and the destination will ultimately get the frame. This process really cuts down on the amount of data that's flooded through the network. It also breaks one large collision domain into a few smaller collision domains. And remember that the smaller the collision domain, the better, as there's a smaller chance of collisions, and less collisions means better performance. The network as a whole can now grow larger than before. The term we use for this is scalability. And because bridges are intelligent, and they look at the MAC addresses, these are layer 2 devices. Now, if you're really thinking, you will be wondering, how does a bridge know where all these MAC addresses are? And that's a very good question. I'm so glad you asked. The bridge doesn't just magically know where all these addresses are. It needs to learn them. So let's just imagine that the bridge in this diagram here has just been turned on. Right now, there are no entries in the MAC table. So a device sends out a frame and it arrives at the bridge. The bridge does a MAC lookup on both the source and the destination MAC addresses, and it finds that neither are in its table yet. So the first thing it will do is it will add the source MAC address to the table, as now it knows where to find the device that owns that address. The destination is still unknown. So, without this information, the bridge has no choice but to flood the frame out all interfaces. That is, except the one that the frame was received on. Let's say that the destination is in the network to the right, and it has now received the frame. It wants to respond by sending a frame of its own, and that arrives at the bridge. The bridge does a MAC table lookup just like it did before, and it sees a new source address, which it learns. Fortunately, now it already knows where the destination MAC is, as it had learned it earlier, and it can send it out the correct interface, avoiding the need to flood the frame everywhere. Sending the frame out is called forwarding. Being selective and not forwarding it out every single interface is called filtering. Let's imagine though that we've picked up a computer and moved it from one segment to another. What problems might we face here? The problem is that the entry in the MAC table is now incorrect. From this, we can see that the MAC table entries should not be permanent. The next time it sends a frame, the bridge will see the MAC address on a different interface and it will update the entry in the table. Take careful note of this. A MAC address can only be learned on one single interface. And what would happen if we turn the device off? Or perhaps it's failed, or it was a guest laptop connected to our network. Well, each entry in the table has an aging timer. When the MAC address is learned, this timer starts counting. Whenever traffic from the device is seen, the timer resets. If no traffic is seen before the timer expires, the entry will be removed from the table. This helps keep the table nice and small. After all, these tables have a limit to their size as well. In summary, bridges have 5 very important functions. They flood traffic out their interfaces if they don't know where to send it. They learn which interfaces to use for certain destinations, and they forward traffic on these interfaces. They filter traffic from interfaces that they don't need to send the traffic on, and they age out entries in the MAC table as they become stale. I highly recommend that you try to remember these functions, especially if you're planning on doing a networking exam. Now, let's move completely into modern networking. Around the mid-1990s, switching was developed, and it became popular by around the year 2000. Switches are the devices that we use today. They bring the best features of hubs and bridges together into a single device. They have a lot of ports like hubs do, so we would typically connect devices directly into the switches. There's also no dumb bus topology inside the switches either. Every single port behaves like a bridge port, so this topology is no longer a bus topology, but a star topology. This also means that frames do not get flooded out the ports as often. In addition to this, switches are intelligent and they support the same functions that bridges do, like learning, forwarding, aging, and so on. Like bridges, as they're intelligent and look at the MAC addresses, they operate at layer 2. A very special advantage to this is that every single port is part of a separate collision domain. That now means that multiple devices can send at one time, and there's very little chance of collisions anymore. This vastly improves efficiency and performance. And for that matter, this isn't a shared bus network. Devices can send and receive at the same time, which we call full duplex. Keep in mind though that if you take an old hub, if you can even find one anymore, and you connect it to a switch port, then everything on that hub, it's still part of the same collision domain. It's still half duplex and so on. The important thing to learn from this is don't use hubs, use switches. The switches handle frames in 3 different possible ways. The first method is called store and forward. The first few bits of a frame arrive at the switch, and the switch stores them in memory. In fact, it will keep storing these bits in memory until the entire frame has arrived. Once it's fully there, it will then send the frame out one of its ports. Store and forward is the safe switching method, as the entire frame can be checked for errors before it's sent out. The second method is called cut through. The switch starts receiving a few bits of a frame and it waits just long enough to see the destination MAC address. Once it's got the address, it does the required lookups to work out which interface to use, and then will immediately start forwarding out the bits. This method does not use any form of error checking, at least not by the switch. All the error checking is left up to the destination device. This makes it by far the fastest method of switching. The third method is a compromise between these two. It's called fragment free. The switch stores the first 64 bits of the frame as they're received because this is the part that's most likely to have errors. If there aren't any errors here, then all the bits are sent out immediately as soon as they're received. Generally, we don't choose what type of switching we use. It's chosen by the manufacturer of the switch themselves. It's not something that you generally think about every day. It might be something you think about if you're buying a switch though. So, what do you think? Why do we call these switches? I kind of think it's like having an old telephone switchboard operator in a little box. When frames come in, they create the path for these frames to take, just like they did with old telephone calls. And really, that's what switching is all about. It's about dynamically creating paths to forward frames. Hubs are pretty rare these days too. Bridges are still around, but they're a bit different to what I've described here. These days, really, switching is the king. Here's another few quiz questions for you to try. Pause the video here and see how you go. Hey, guess what? It's time for a lab. I told you we'd do a few of these. I'm running this lab here on Viral. I'll make these lab files available on the website, and I'll put the link to that in the description. They'll include the running config files, so you can use them in any lab. You don't have to use Viral just because I am. Right, we're going to start with the simple topology. There's just two switches, they're connected together, and there's two Linux servers connected to each one. Only one server is turned on at the moment. I haven't put any special config on here. There are just a few defaults that Viral has put on for me. And we'll be working just on switch 1 throughout this lab. Let's start by getting an overview of our interfaces with Show Interface Status. There's not too many interfaces here, after all, it is only a lab. A real switch would have plenty more. You can see the port, which matches the diagram over on the left. GI is short for gigabit. Cisco named their interfaces after the faster speed that the interface can handle, so these can do 1 gigabit of throughput each. On some of the older switches, you might see interfaces labelled FA, and that's short for Fast Ethernet, which is only 100 megabits per second. On some switches, like this one here, there is only one type of interface, while others, you might find a mixture of different speeds. You might find some Fast Ethernet, some gigabit, you might even find some 10 gigabit interfaces. The name here, that's the interface description. We discussed that in the last video, so nothing fancy there. The status column shows that all our ports are connected. If they were disconnected, their status would show up as not connect. Don't worry about this VLAN column for now. VLANs are very important to us, but we won't get to that till the next video, so just ignore everything VLAN related for now. And finally, notice that these ports are all full duplex. That's normally what you see with switches. If you connected an old hub here, you would see that change to half duplex. Alright, so moving on. Let's have a look at the MAC address table. We've talked about this table a lot in this video, and now you finally get to see one. It's a bit boring right now. It's only learned one single MAC address. The type column confirms that we've learned it dynamically. That means that we didn't manually configure this MAC address in the table. The interesting part is the port that this was learned on. We can see that this is GI11, which is the port that the second switch is connected to. This brings up an interesting question. Do switch ports have MAC addresses? After all, they're just there to forward the traffic, right? In most cases, yeah, switch ports do have MAC addresses, but that depends on the features that the switch supports. Some features require one switch to communicate directly with another switch, so they need MAC addresses. We'll see some of these features throughout the series. But that's not the whole picture. Switch ports may have MAC addresses, but they don't need MAC addresses to forward frames. Take a frame that server 1 is sending to server 2 as an example. In the Ethernet header, the source address will be server 1's MAC. The destination address will be server 2's MAC. The switch port does not need a MAC address in order to forward the frame. Does that make sense? I hope it does. Let me know in the comments if it really doesn't. So the next question we have, where is server 1's MAC? It's missing because of the aging timer. Let's see what this timer is set to with show MAC address table aging time. And here we can see that the timer is 300. That's 300 seconds. When a new entry is put into the table, it's given a timer. The timer starts at 0 and starts counting up. So server 1's MAC was learned, and the timer counted up to 300 seconds. And its MAC was removed from the table. Behind the scenes, I'm going to access server 1, and I'm going to generate a little bit of traffic. Now, if we look at the MAC address table again, there it is. Server 1's MAC address and the port it was learned on. So just for a bit of fun, let's change the aging timer. We'll go into configuration mode and enter the command MAC address table aging time 900. That sets the timer, as you guessed, to 900 seconds. And let me just say, I don't normally recommend changing this timer unless you've got a pretty good reason. Mainly, I'm just trying to show you that you can. Now, let's turn on server 2 and we'll see what happens. It might take a while, so I'm going to use some special video editing to speed this up. And it's on. Wasn't that quick? We can see the entry in the MAC table. So what does this teach us? It shows us that most devices will start sending traffic of some sort as soon as they turn on. And as soon as they do this, the switch learns their addresses. I'm now going to fire up the remaining 2 servers. And when they come online, they're added to the MAC table too. And notice that they both appear on interface GI11. This is the interface that's connected to the second switch. This happens because the second switch has forwarded traffic from these servers. Perhaps they were trying to send traffic to a MAC that doesn't exist, for example, and the frames would have been flooded out all ports. Therefore, switch 1 will have seen the traffic and it will have learned from it. Something that we can learn from this is there is no problem at all learning more than one MAC address for a single interface. How about we try adding some entries to the MAC table ourselves? It's not something you do very often. In fact, I can't even remember the last time I've had to do this. But it's good to see that you can, and of course you want to have a bit of a play with this, so let's give it a go. While we're in configuration mode, enter MAC address table, and then static, as we're entering a manual or static entry. Then we need the MAC address itself. I'm just making up a fake address here. We need to tell the switch which VLAN this MAC belongs in. Once again, don't worry about this too much for now. We'll go through that in the next video. And finally, we add the interface that this switch should use when sending frames to the MAC. And here's something just a little bit interesting that I'll bring out while we're seeing it. Do you notice that the command we've typed is too long to fit on the screen? The CLI adds a dollar symbol to the start of the line to show there's more in the line than it can show on screen. Just thought I would bring that up while we're seeing it live here, because I know that many of you will be new to the CLI and might not be sure what that's all about. So I hope that makes sense if you see that now in the real world. And now if we go and have a look at the MAC table again, we can see our new entry. But imagine that there are hundreds of entries in this MAC table. And this is a very possible scenario on real switches. It can be difficult to find a particular MAC that you're searching for. What we can do is we can show the MAC table and we can add the address keyword followed by the MAC address that we're looking for. And the CLI will filter the output to show only the MAC we're searching for. Isn't it clever? And speaking of having hundreds of entries in the MAC table, the table doesn't have an infinite size. In fact, it's a data structure in memory called a CAM table. CAM means content addressable memory, and it's a special storage space in memory which is optimized for this kind of data. As this is limited in size, there's a limit to how many entries will fit in there. And we can see this with show MAC address table count. And right at the bottom of the screen, you can see how many more entries can fit into the table. It's quite a large number in the lab, but a lot of real devices will have a number significantly lower. If you do run out of entry space, and then a new MAC address is learned, the oldest entry will be prematurely aged out to make space. If this is something you're seeing in the real world, you either need to redesign your network or buy bigger switches. Let's try manually clearing this table. Once again, Don't generally do this in a production network, because then it would have to learn all the MAC addresses again. But, sometimes you might have a good reason, so it's good to know that you can do it. Alright, we have 6 entries here, 5 dynamic and 1 static. So let's clear those out. Hang on a moment. I can't find the command that I'm looking for. Oh, yep, okay, sorry, I'm using a show command. What I really need is to type in clear MAC address table dynamic. You'll notice that there's no option for static entry clearing. If we look at the table, we can confirm that the static entry is still there while the rest are gone. In fact, this can be your homework. Work out how to clear this static entry out of the table. Download the lab or build your own and have a go. And that brings us to the end of our lab. Let's finish off with a few quiz questions. I've tried to make these a bit like something you might see in the exam, so hopefully these will help you out. And hopefully after we've been through all this, you can see why we have switching and how it works. We will take this further in the next video. We're going to have a look at the concept of VLANs, also known as virtual LANs. I highly recommend watching this. This is something you definitely will need to know. Please like the video if it has been helpful, and share it with someone else who can benefit. Thank you, I will see you in the next video.